Hi everyone. So 2 minutes later, so Dr. Chen still cannot get access to the internet. So uh, because time is limited, so how about we just first start our discussion? So hopefully Dr. Chen can join us before the meeting ends. Okay. So hope everyone goes well in the last 2 weeks. So last week, uh, because it is a spring break in UMass Dartmouth, so we do not have a discussion. So this week, you may ask questions first about lecture 7, and then about lecture 8, which is lecture 7 is a sediment module. Lecture 8 is a wave module. Oh, Dr. Chen is here. Great. So this morning I received the email from Yunji. So
Recording in progress.
Yunji sent me 4 questions from Professor Wu's lab. So how about Yunji? You start from your side.
Oh, okay. I will start in my question. Uh, in lecture 7, they said morphology module used in FVCOM get the method from Rowing 2006. And I searched that paper, and this paper described 4 methods to calculate the morphology change. And in my understand, FVCOM use the third method, morphological factor. I uh, and I in my understand, all 4 method is focused on the showing long-term morphological change with limited computational resource. So if the computational resource don't have the limitation, which method is most better for calculate some bathymetry change.
Okay. Okay. Yeah, I couldn't remember so which method we use right now. To be honest, So then, I think it's no, I couldn't remember which. To be honest, I don't remember. They got a four method. We need to go back check the coding, see which method we used. Okay.
Okay.
So I probably not able to answer your question for this one, right? The method we do right now, it's like a, you know, like a, use that's why most of just driving, my understanding, is driving by sediment, basically by sediment layer. So because sediment accumulation, so we use that and to determine how how the water level changes. So we didn't use the four for sure, okay, but I couldn't exactly remember which one is. Let me, okay, Siqi, could you write down a question? Okay, then after that, I can talk to you. We can send it to Dr. Ge.
Yes.
The person has been coding this sediment model because I think Jeff Kober was do the first time for some other just but Jeff Kober did not run in the way and FECON coupling. The way and FECON coupling later is Dr. Ge was doing some work. So probably ask Dr. Ge answer the question, then we can review the question for next week, then open the coding, see that. Okay.
Yes.
Yeah. So I need
And
Dr. Ge, okay. But I do test that one when we used to try to see from Changjiang River. We had a typhoon passed, so we turn on the wave current and sediment interaction. So we want to see how much morphology changes, how the seabed changes. So we found out after storm passed, it's not a very significant. We only took a 2 centimeter changes. 2 centimeter changes, just because no, most of not happen in the coastal region, most of happen near estuary region. So had locally they can accumulation sand, they put a sand, put accumulation. It's not a significant, only 2 centimeter, I remember. So we try to write a paper said, okay, if you know, because you had a stone surge model, so you had a sediment, because every stone surge come, they was push a lot of sediment to put against the coast, right? So after against the coast, we feels like if you second day, couple day, you get another hurricane come here, your precipitation changes, right? So you see, your surge level could be different, right? Because your precipitation changes, flooding, like a flooding type, flooding water level, the surge level could be much higher. So that's why they had many years ago, they had two typhoon very close. Okay, they found some information. Then we run the model. We found only 2 centimeter changes. We didn't see the first, but also found locally, not a whole system changes. So we still don't understand what's really going on. That's a very good topic, okay? Right? So you look about it, every time you use a stone surge model, you make prediction. You always find in the model how underestimate like a surge total level. So you look at every time, you look about, like a constant shifting. Every case you run, constant shifting.
Hi.
So that means
Yeah, I'm in a meeting.
yeah,
How are you?
that means the total mean depth it changes, right? So after storm. So the question is how it changes, right?
Yeah,
So then
Professor Chen.
yeah, sorry.
Yeah, Professor Chen. Yeah. So not just storm surge. I think we feel a lot of uh bathymetric change
Yeah,
caused current change in near harbor.
yeah,
So I think probably Professor Go and
yeah,
we could maybe have a kind of separate meeting.
yeah.
And Professor Chen, as I said before, we don't know how many students have a question. So why don't you listen to all the questions first, and
Yeah,
then
just like yeah.
arrange your time.
Yeah, that's good. Like that's Dr. Lee as we answer. So yeah, okay, that's good. No, yeah,
Oh,
Dr.
Dr.
Lee,
Lee,
you
Dr. Lee,
organize,
Yes.
okay? You're organizer, okay?
yeah, Dr. Lee, please organize in that way because we have a very limited time, and we don't. Sometimes Professor Chen explains, and he kind of concentrate on that
Okay. Yeah.
answer, and you know what I mean.
Yeah. Thank you for the suggestion. So, let's go to the next question.
Oh, okay. I also have a question about the assignment of sediment module, and in the INP file, there
So,
was a
Dr.
comment
Lee,
like this.
Dr. Lee, would you pop up all the questions in the screen,
Uh,
and then maybe all the students could um, uh, make their questions first
Yeah,
because we cannot see any screen now.
yeah.
Now is Yunji's screen.
That's the UG screen. It's our not
Then I will stop sharing my screen. Okay.
So Yunji, yeah, your question is finished, right?
yeah,
Oh, actually, I have one more question,
yeah,
Yeah.
you just post that, okay?
but it's okay.
No. Yunji,
Okay.
would you share your screen then?
Yeah,
Okay.
show your
Yeah.
screen because
Oh, and
I can see the screen.
yeah, the first question was this, and I have two more questions about assignment.
Mhm.
If the morphology model, even F of the bathymetry change are considered to calculate some current or density or something like that. I want to know, is it right or no? And I checked the offline sediment file input for file, and I see some value about the sediment. So I want to know how we can make it. Is this offline forcing file made by pre-simulate of the sediment model?
Mhm.
Okay,
Mhm.
that's my question.
Mhm.
Yeah.
Okay, I stop sharing.
Mhm.
So, Min Woo Park, could you please start your question?
Okay. Okay. I have a question. During this course, I read this paper. The paper compared to current wave sediment model.
Mhm.
The two models shows
Mhm.
difference in bed thickness, and
Mhm.
the
Mhm.
paper explained that this difference were due to the parameterization for the current wave interaction.
Mhm.
Since the current wave interaction differ, I
Mhm.
think that wave variance caused by current would also vary, which in turn leads to difference,
Mhm.
erosion, and sedimentation outcome. Also, what difference between the two parameterization cause cause variation in how current affects wave and lead to different sedimentation results. This is my question.
Okay.
Okay, thank
Okay,
you.
thank you.
I think Jin Yong Kim, I also received a question from you. Could you please start?
Okay. Can you see my screen?
Yes.
Uh, okay. And S-Wave, SWAVE used the spherical stereographic coordinate system conversion to avoid the singularity issue at the North Pole. And it calculates the directions of the wave spectrum, ambient current velocity, and wave group velocity on the stereographic coordinates, and convert these variables back to the spherical coordinates. But if I take the global FVCOM grid in stereographic coordinates as an example, because of the characteristics of this coordinate system, the grid shape is relatively well preserved in the northern hemisphere, but becomes increasingly distorted toward the southern hemisphere. So I can't understand how stable calculations are possible under such conditions.
Mhm.
Okay, thank you. I Gmail Seal, you also have your question, right? Could you start yours?
Yeah, I share my
Mhm.
screen.
Mhm.
So my question is in lecture 7 on slide 2. Uh, the professor explained that when the sediment suspend, if the critical shear stress tau c here is exceed, then I understand that the critical shear stress is an experimental value. So critical shear stress is only one value from experiment, but we should make 3 input files for sand, silt, clay. So is there any special know-how to make this input file is my question.
Okay, thank you. Jin Yong Kim, here I received another question from you. So do you change your question or do you still want to ask that one?
Okay, wait.
Sorry, I'm
So my another question is here. The calculate of bottom stress is 2 types, and pure flow stress and current wave sediment interaction stress is here. But I know that the FVCOM sediment model is coupled with the wave model. So I think current wave interaction is very good for this equation, but why we need to pure flow stress bottom stress is needed. I don't understand that.
Mhm. Mhm.
So is there any other question from Professor Wu's lab?
Mhm.
Okay, so I see in the chat, Ikro, you have a question. Could you please read it up?
Yes, can I share my screen?
Yes, please.
Yes. Okay. So I have a few questions. So this
Sorry,
is
I cannot see your screen.
sorry.
Yeah, sure. Show your
Yeah. Can I see that?
Wait, yes.
Yeah. So in here, so first I want to direct some slides. So here, first one is about the density equation, and in the lecture, it mentioned that wave current interaction has two ways to calculate the stress. One is with the radiation stress, and one with the vortex stress. And also in another slide, it said that it can be, there is two solver. One is explicit solver and another is semi-implicit solver. So when I went to the mac.inc file, so there is the commands so that we can decide while we want to analyze the wave current interaction. So I have few questions regarding that. So first, as there is two type of stress, if I turn off the vortex force, that means by default the radiation stress has been calculated. That's my first question. Then same as if I turned off this flag 34, then is it means that semi-explicit solver has been applied? And between the semi-implicit and sorry for this one, it's implicit. So between the explicit and semi-implicit, which one is the better one? And if I want to analyze wave interaction with the offline wave model, so along with turning on the flag 37, should I also turn on any other module? Like obviously flag 32 will be turned on, but shall I turn on the flag 34 as it was already opened in the exercise file? And another one is if I want to analyze the wave model, only wave model, that is SWAV model, then is it the flag 35 should be turned on? I mean, I'm a bit confused, like which flag should be turned on? And can you explain me what flag 36 and 33 is? So basically, I want to know how these flags actually work in terms of wave current interaction and which one is applied for what. And I have another two questions. Can I ask?
Mhm.
Yeah. Okay, thank you. So I had a model which is a wave current interaction model with the online coupling. It's an online coupling. So I have seen that with the change of this value NSDLTC in the input file in SWAN, the significant wave height changes very differently. So if you see when I'm increasing the value from 2.5 to 30.5, the value shifted, the significant wave height value shifted to the leftwards. So this is my peak significant wave height at the time of around uh, around 17 January. So black one is the what I want to expect, but the yellow one is when the NSDLTC value was 2.5, and with the increasing value, it shifted to the leftward to the expected value. But what happened is when I'm change the value from 25 to 30, the value is very disruptive in here in the initial time, as you can see in here. So my question is, I understand the model is not the model is now very unstable in that state. But my question is, why is that so? And I have changed multiple other parameter, other interval timing or other interaction parameters, but nothing changes the significant wave height except this parameter. So why this parameter is so strong in terms of wave current interaction? And I'm not sure if you can answer me this one or not. This is the paper I have gone through a while ago. So this is paper of Gyo Donggao, and he did some experiment. So I was wondering if I want to do the similar kind of experiment, uh, can you please explain me, or do you have any idea that how can I achieve this? I understand this is not your paper and this is not I believe that I'm not sure if you went through this kind of research or not, but if you have any answer, I'll be very glad to get it. Thank you.
Yeah, thank you. Any other questions? So if not, Dr. Chen, which one would you like to start?
Yeah, I can, first question, the couple question related to sediment. First, the some question related to coding, that's why I already explained. Okay, we need to talk to girl, what is show, what is for what the method of, could you post the question again? Okay, let's go through the question one by one.
Mhm.
So this way, we have to be check with the girl, see what method we use. Okay, the second one, your second question. Okay, so we need to send your question to the girl, let he answer.
Mhm. Yeah.
Second question, could you put his second question? Second question here, just like how the morphologity factor you use, so this also, what I understand, if you pick a fork, that means the morphologity model is not on, okay? Not on, okay? That's what I based on my understanding, but we need to double check with the girl, okay? Make sure everything, my understanding is correctly, okay? Right, okay? So, if you put a force, you probably still on, but probably don't calculate it, okay? Let the girl to answer the question because I didn't run the same model before, okay? Girl run the model, so he probably know that. He should know this answer. Okay, third question. Third question here, so that's why that's the default value over there. They get a force, the coherent sediment. So that's the whole things I think I'm pretty sure come from Ron's model default setup. But we can ask a girl to give you answer the question, okay? Because he run the coherent sediment model before, okay? So that's why we can leave you a question. We can give you answer next week. Then the second person question, this one. Okay, parameterize difference is because the wave model different. Okay, there's a wave model, but hydrodynamic model is different. That's the difference should be very small because for structure grid, because this is both structure grid, okay, rectangular. So unstructured structure grid should be no any different to show this kind of the circulation. But most of the circulation come out, FVCOM use the S wave. That's wrong. Was use the swarm because swarm model is the first order approximation model, the wave model. Then FVCOM S wave is the second order approximation. So that's why accuracy is different. Okay, that's why the wave structure not only parameter difference because that's wave is doing the coupling, so two-way model uses one here comparison. So the one is the first order approximation, a second one is second order is different. The second difference is but because when the current interaction we use the radiation stress, but radiation stress had a different version radiation stress. George Miller developed so many methods. There are 2005 version, 2008 version, it keeping changes. Okay, so most of the changes you need a surface, how the vertical profile, so radiation stress like this way. So the formula is different. This can be costly different. Now, so we very hard to say which one is better. So, I don't want a conclusion that FVCOM better than wrong. I don't want to see that because that's not everything there just because you don't have a, real data compare. But look like a pattern similar, right? It's similar because most things like like a FVCOM model, the basic thickness, because this quality is obviously be confusing because they say the X, Y, 0, and the weird coastal region, okay? But just on the downside, you can see much stronger than the wrong, okay? So that's different. So I couldn't give you, I can see why cost different, but I couldn't tell you, which one is better, okay? Because all the idea is testing, so we don't have a network solution can compare, but they do show the difference, okay? All right, another question. So this one here, okay, answer question is no. If you run for non-coherent model, you include one segment type in the one run. You have to run, for example, you run for sand, you have to run the sand. You have to run the theater, you have to run the theater. You have to run the crate, you have to run the crate. Okay, so you're not able to get the three things mixed together. However, you only can do that when you turn on the coherent segment module. Now, if you do the coherent segment module, you can put all three together. You can choose what segment type in the default file. You can have a list table there. You show you what the define there. So, but you must turn on the coherent segment. Otherwise, you have to run one by one. Okay, right? So then your question is how you calculate critical stress. That's a very good question. Most issue for segment model is how to determine the critical stress, the bottom stress. Okay, so like we did before, some people like a constant uses the value. Okay, just make just the equation go down there. So they use the bottom stress. They put some criterion for each type of sediment. For example, they had a table show laboratory experiments. Or what is you could have done, but you don't see this one here. So you had to get a bottom stress. You had some coefficient. What is the critical stress? Okay, critical stress. This coefficient is determined by laboratory experiments. Okay, just for sand, they had a critical stress number. So for silt, you had a critical stress. For the clay, they have, but they all specify. Okay, for certain material, but however, the critical stress should change space and time. But you put a constant there, you're not able to simulation sediment correctly. There's some people tune the number but not correctly. That's why we has been determined the critical stress. You know what we did? We had an inverse model. So we used South Korea stationary satellite. Stationary satellite. Now South Korea has stationary satellite in the East China Sea. They keep stay there to see the sediment. So we use like a one-dimensional, okay, the sediment model to use the satellite prediction suspension sediment concentration, converts back, see what kind of critical stress you need to have to create this kind of sediment. So that then you can create like a special function with a critical stress. So each node, you get different stress function. So then you put in the model, you get a better result. Okay, so it's tough to do that. The best way to do this, because you need to consider time dependent, the critical stress, because it changes, particular coherent sediment, okay? So they get mixed together, you get a clay, you get a sand together. So you couldn't just, you couldn't just simply say, okay, that's the sand critical stress, that's the changes, right? That's the sediment model is really challenging to get it correctly. That's why use like stationary satellite, determine the stress. That's probably most the best choice you should do. Okay. So I can say probably we can download the paper sent to you how to do that. Okay, we had a paper project JGR show that. Okay, so probably you can find out to send to you the paper. Okay, next question. Okay. That's a question is to talk to you. Okay, that she said since FVCOM sediment model is called the way model, when do you use pool stress? That's a good question. So some people, if you run it for seminar model, some people run seminar without turn on the wave model. Okay, some people, when they do the seminar, you should turn on the wave, right? The wave interaction. But a lot of people do seminar, they don't turn on the wave model. Okay, if you don't turn on the wave model, so you don't have a wave parameterization, so you have to use the purely, the circulation stress. Okay, so that's the reason. You see me? If you turn on the wave, you should use like second parameterization. Okay, if you include the wave current interaction, you have to do that. But sometimes you run a seminar, you don't turn on. You look at the previous lot of paper, they don't have a wave model include. Okay, that's why you have to force a choice. You have to prepare the case. The people don't turn on the wave. Okay, do I answer your question?
Sometimes it takes too much time to simulate together. So sometimes people run the wave model first and
Yeah,
then
so
get the wave.
then put a parameterization there, right? That you can do. But some people just even don't include that, the wave parameter. Just because this parameter you see here, linear causal, had a correcting point into a log layer. So that's the kind of things to put it there. Three things, they can change the parameter. CD number, they can counting indirectly, okay? But if some people run the same model first, then you change the second method here, you input the data in, just like Professor Wu said, okay? Answer your question? Then get the next question. Let me answer a question if you don't. Okay, that's an interesting question, I tell you. So there are two issues here. One is North Pole synchronality, right? So that's the issue. So you have to do. Second one is high latitude conversion. Okay, later high conversion, because of the wave model, they assume each cell, the wave direction propagation not changes. Right? So when you go to when the latitude higher than 80 degrees, 85, 80 degrees, so this latitude, changes significantly, quickly. But your resolution not enough, you assume the whole cell, not let the wave direction change, so you can get a wave conversion. Okay, so we had two issues here. One is a synchronality issue, one is the converging issue. So the method, we get a projection method. Okay, you see the projection, we changed the coordinate to equator. No, not for this formula, okay? Another for change the equator. So then you change the equator, so make it so we can define, like a wave can change the cell direction. So make a correction for this solve the converging issue. Okay. Then the second issue is the synchronality problem. That's only the node point, couple point. But a big issue is to do that is the converging issue by the wave model. But FVCOM don't have a problem. But FVCOM, is great. They like the velocity change direction, but wave model don't. Okay, that's the whole thing's the method we use just for wave model. That's two issues. Okay, that's why it's not. So that's not just what you're talking about here. The global uncharged wave model. You do the ocean circulation. When you do the here, so for ocean, you only need a couple points to solve the problem. But this projection method only for 8 grid point. It's not for larger grid point. That's why you have to therefore design this. But for wave model, they have the projection. Okay, you see the Southern Ocean. Southern Ocean, don't worry, because Southern Pole is the land. Okay, you don't have a synchronality problem for Southern Ocean. Okay, because Southern Ocean is the land. Okay. Another question. So this one, okay, flag reasons. I think we need to double check. We can give you answer because I couldn't probably give you because this is so detailed for coding. So I probably need some people in my lab to give you right answer for next week for your question. okay, answer your 4 question here. Just how to turn on, how to turn off, which turn off will mean for that. So I can ask NLP answer your question, okay? Because this is a lot of detail for make a selection. I don't want to see something wrong, okay? I can ask some people answer your question. Okay, so this one here, I need to, because I long time not wrong, I need to answer my people wrong way more to answer the question, because MS, like a parameterization, you choose there. So I need to go back and find out what definition they are. Probably next week, I think I can give the question, Dr. Lee can give it to Dr. Chi, send Dr. Chi, ask Dr. Chi answer the question.
Yes,
Let me
sure.
we post the question was on the on the the board, on the discussion board,
Yeah.
the quiz board. So if Lee can talk to Dr. Xi, so probably Lee can explain to next week. Okay.
Yes.
So yeah, this paper, this is a Xiao Huang Wang, the paper. So I don't have a lot of suggestion to do that. I think about most issue for this paper right now, they use the constant critical stress. That's why I was think I really want to do the good sediment imaging. I was really suggesting to use like stationary satellite data, determine because most sediment model really critical, does it get sediment correct, not correct, is a critical stress. How suspension happen, right? So that's a critical issue, but you have to get a special and a time-dependent critical stress determined. But best way to do that is use the South Korea stationary satellite. South Korea had a lot of advanced technology. Okay, you probably not realize that. So now had
Actually,
two countries had a stationary satellite. One's the U.S., one's South Korea. But South Korea is open. South Korea, everybody. So U.S. you had to require to ask them to give you data. But now they focus on the Gulf of Mexico. You had to like satellite located one location, continue to management. But beauty is because station satellite, they keep a location for all time, just a snapshot, for every 6 hours. That's why you get a time series. You can really build like a special and a time dependent critical stress. Okay.
so actually, Professor Chen, there's a second GOSI 2 is now working, and we have very detailed information from the satellite. And because one of my colleagues are working with that specific project, we can even get the data which is not open. So it is very interesting. And I know that you publish about kind of solving that inverse problem using the GOSI image. But
Yeah.
as far as I remember, the paper around, yeah, I just got it, 2020 at Journal of Marine Systems. In that paper, they don't really describe how to kind of how to solve that inverse problem.
And then you had
Spec-
another paper.
oh, it's not this
So
paper.
I think they had one paper to measure the matter, another paper because a girl, he want to get promotion, he keep him publish a paper and a
I see.
similar topic. Okay.
I
So
see.
they
I
had
see.
one paper had a one-dimensional mathematical equation. I showed a paper. I probably don't have a paper, but I don't know, I still keep here, but I editing the paper. Okay, so I don't know the paper here. So I don't know, so probably too long. I probably got another computer. I don't put it here anymore. But at least you can see they had a one-dimensional equation. Use the inverse to determine the critical stress. So use the image data.
I
Okay.
see. So that will be really, really important, as you said, the kind of inversely calculate or determine that critical shear stress from the cellular image will be really, really important.
So if you don't do that, you very hard to get a special distribution sediment suspend sediment corrected in the region because this stress change with space and time. Almost the sediment model right now is a constant critical stress, particularly when you consider heavy sediment, right? The interaction together, different type of the sediment. So it's very hard to determine, because of every stress, because sand, they consider sand, right? So clay, they consider clay, okay? Right? They consider silt, but this all stress is non-interaction. When you get an interaction, then include the clay in there, all is critical stress. Right? That's why you very hard to determine for mathematically. That's the reason best way to use the satellite data because satellite now the station satellite they get a snapshot. Most I know before it's every 6 hours. Probably now it's you get a new one probably a more short time, right? So you can use this one get a time, special distribution critical stress also time dependent critical stress.
Actually, another question is because, as you said, there are three types of sediments,
Yeah.
and each model requires each critical shear stress,
Yeah.
right?
So
So,
if you don't turn on the cohort sediment, you have to run for each. Only can run for one. If you only get a non-cohort sediment model, so you only can run one type sediment. Okay, so they don't have interaction. But when you turn on, cohort sediment, you see our homework, like a home testing. So you got a default file. You can select the type of sediment.
yeah, but usually, for example, in our case, it's always when we go to the field measurement, then it is always a kind of mixture, sand,
Yeah.
mud, clay, right? So we usually choose three types
Yeah.
of the sediments, and then the problem comes out that we have to give each specific critical shear stress for specific sediment type, and we don't know
Yeah,
that.
but that's why you can for each type you can find it for textbook. Okay.
Yeah,
For
right.
they get a parameterization. You look at our old paper. I probably Cetala River. So we run the three, three. We just get a quick stress from the laboratory experiment. You send how much it is. Set was the issue. They had a number. Okay, but it's all constant. If you run a
Yeah.
small S3, it's okay. If you run it for larger region like East China Sea, like a Changjiang River, like this way, you couldn't use that. Now you can tune the model, get one station compares good. That means you said the model is correct. Right? The only way to solve the problem, a lot of people spend a lot of time to solve the model, none one very successfully, to be honest. Right? It's not because they're not smart, because critical stress is a really issue you have to solve. Right? But this one, you're not, so it's time dependent, spatial dependent. So only way you can solve the problem, just use satellite data can help me. But I don't know, so that's perfect. At least it's better. Okay. Okay.
Is it possible to have a kind of this kind of online meeting with Professor Go?
Yeah, definitely. Okay.
Uh,
But I need to find the time available. It's good way so we can invite him, but we can invite him to the next class. Sometimes Lee can ask that he's available. Let him
Yeah.
to bring the sediment issue.
uh-huh.
Okay. Yeah, we can
That'll be
for your lecture. We can invite guests, people. You see,
yeah.
my syllabus said we can invite him, so you can invite him to come to talk about this.
Mhm.
Right?
That'll
We
be
can invite
that'll
him.
be really that'll be really nice.
Yeah,
Yeah.
but we want to make sure he's available next Thursday. Dr. Lee can
Yeah.
check. Okay.
Right.
Yeah. I received another question. I'm not sure. This one. May I
That's-
know?
No, this is not this one. This one, this one we talk about, for the vegetation module.
Yeah. So may I know who raised this question? I received it from email, but today no one raised it. So do we
Actually,
still need?
Yeah, that was Junyoung Kim's question, but he changed it.
Oh, okay,
Okay.
okay. So do you still have question about this one?
No, that's one. Oh, that's one. Okay, I didn't see that. Oh, this one. What question you have?
Okay, so
Geomil,
it,
How,
in
how can affect vegetation on the water temperature? Okay, calculation. Oh, okay. That's a question. Okay, you look about the paper, and they talk about how the vegetation. Okay, you go back to the paper. So you have a mathematical measure, vegetation, the couple thing. You know, I know you have a paper. You have this one. No, go down, go down. Okay, go down, go down. He probably don't. This is okay. Go down. Okay, yeah. Go look here. Okay, I wait. You can you make it bigger? Okay. Most of the vegetation we have, you know, change. No, he don't direct fix the temperature because they like a plant. That's why they get a drop in stress in the vegetation. They use the formula, the calculation. You know, they present the only change about roughness, the mixing. Okay, they change this one here. You see the parameter. They change this parameter in also change the way. That's all the parameter changes. Most change is dynamics, not direct the temperature. Then dynamics changes, mixing changes, transport changes, they affect the temperature. Okay, because you know, you have a vegetation, velocity becomes weak, right? Vegetation, you are there, velocity becomes weak. Velocity becomes weak, the resting time becomes longer, right? So you look about a picture, I show you. That's a very nice, observation. You see here, you know this, you look at time series. Time series picture.
oh, sure.
The first picture, yeah. No, you just the picture you show this one, yeah. You can you make it bigger? You see really happen. You know, when you include vegetation, very interesting is when the flooding tide, they take a long time get the water into the marshy area. When the tide drop time, the time transition very short. You see the direction over here? Go there, quickly go down. Okay, you see what will happen? They quickly go down. That means you can see that is sediment concentration. That is what could you make it bigger? So yeah, you look here. Okay, that's the current direction. You look about here, that's the velocity. You look at the velocity. Okay, you go there. So you go there, gravity goes there. Okay, they certainly can shut down. Then this phase, all of this becomes dry. Then dry, they don't have velocity. The next time you get another phase come here, they shut down. That's that they get an apple tide, moving more faster than the flooding tide.
Professor
Okay.
Chen,
Yeah.
Professor Chen, we don't know where you are pointing. Would you tell me one more time?
See here. You look at the direction here. You see the direction here? I draw a picture
Can
here.
you
see-
can you point it out?
Yeah, go down. You see here?
No, we cannot see your point.
Okay, let me see.
Okay.
Could you change the color? I can see the red, yellow color.
You see here? You look at the direction. You see certainly they have a 27 degree. Then they kind of very short time, they can change, you know, to the 90 degree. You see here?
Mhm,
Very
mhm,
short time. So that
mhm.
means that you have a currents, you got a currents over there, you get a flooding current, the currents become larger. When the current drop down with the top, they very quickly. I draw the picture you see here,
Mhm.
right? So that's why you include vegetation. So when the water get in, because vegetation has drop stress, they get slowly down. When the water drop out of there, they're moving really quickly. Not like with tidal cycle. Most of the we get tidal cycle, something like this. You know, something. See, you look at sea level. Oh, go up. The sea level. You see what the sea level? You see, this is the sea level go down. This is becomes dry, right? Becomes dry. If you look at sea level, they didn't see much different like this. but you look at currents, it changes quickly. Most of the direction changes very quickly.
So, Professor Chen, are you talking that the vegetation effect on the flow was different for flood and ebb?
Yeah,
Is it different?
yeah.
Why would it be different?
Include vegetation also wave interaction, okay? Because you get a sediment push, okay, onto salt marsh. You see here sediment go down. You get a sediment, you see, you get a sediment accumulation go there. So then quickly when the water drop down, right? They all sediment already be keeping keeping into into the marsh area, sediment deposit there. So then they drop down the current can be really quickly, sediment drop down very quickly. Okay, the next time you're gonna push another sediment in there. That's the reason you get a marsh area, get a some marsh area get more and more sediment. They will pile up,
Oh, I see.
right?
Oh.
That's where you need to include vegetation, okay? Because vegetation can change the wave. They can make the wave propagation slow down. They also make the currents can slow down, right? So this whole thing can be affected like the increase asymmetrically, okay, for tidal current during the flooding and ebb tide. Okay, right?
I originally thought kind of simply that when there's a vegetation, it might behave like a drag.
Yeah.
But because it's a drag, it might be affect to the same to flood tide or ebb tide. But you said it's not true.
No, I mean, so they increase asymmetric. They definitely slow down the current, but they're more affected by flooding tide because you could include sediment.
Okay, I see.
That's the real observation. So that's the reason we do. If we don't have a vegetation, we not resolve this. We don't resolve the fast tidal transition, right? That's why we include sediment, vegetation. We resolve that. Not perfect, but at least we do something, right?
Is it kind of a site specific, or it could be kind of a general?
I don't know because this come from the most tidal estuary. If you go to like an open ocean, like a coast region, they probably phenomenally different because they get a much larger scale. But that's one because you get you look at the picture you down. Okay, I can show you where they are. It's I don't hard to say. You see here, you see. Let me clean what's here. Okay. You see, you look about this quick assessment here. You see, from here to here is different because this here is much stronger tidal inflow, right? This one's very weak branch. The water go every direction. You see, that's all.
We cannot.
Yeah,
we cannot see your point.
Yeah, no, okay, I forget. I forget. You see, you look about this picture. Now look at this. They show you what time he do the measurement. You see, that's the one. He said that's the high level. You see that's one here. You see that's also high level. You see that's for the velocity. A and B, the different K. You do see that. This here, right? They get a much stronger, much wide. Estuary, the creek. This here is much narrow, right? So behavior, because they had a lot of branch here. You see what I have coming here? This had less branch. So how does it behavior, does this, you see this generally or not, it's very hard to say. Right? Because they only had one point of measurement. I'm pretty sure the measurement is here. Can you show the location for observation? Yeah. No, they had a map show observation. Yeah, you see, that's
this one,
yeah.
S5, this one.
I think the observation is here, right? This is here, correct? That's a here. No, that's not a here. It's for something from here. You see here, that's big one. But a lot of small one here, you don't know how they behave. Right? I cannot see this generally. Okay. Okay. Okay, now it's time to pass. Okay.
So is there any other question?
If no question, I think Dr. Lee, you will send an email to the girl, invite him to come for next Thursday. Okay.
Yeah,
if he,
sure. I will send an email to ask him if
So
he's available. Yeah.
we can let if we get a next Thursday, we can ask him to give a simple explanation seminar model.
Mm-hmm. Yeah, sure.
So that's because most of the question for seminar model. So maybe next week. So if he can come, please ask him to address the question first. Then ask him prepare for other question related to sediment. So we can focus the next week section for sediment.
Okay. Yeah,
Right.
sure.
And Professor Chen, you said that the inverse problem paper was published in JGR?
I'm pretty sure it's JGR.
Okay, okay. Let me take a look. Yeah.
I think it's JGR. I probably can find it for you. No, you look at FVCOM website. We get all
Yeah,
people.
yeah.
Do you remember which year, Dr. Chen?
I had a photo because I had all the different version because I editing the 3 times. That's why I had an old version, but because I had an old computer, I get a new computer. I only put a recently file in there. I didn't find the paper here. But I think
Okay.
that's you go there. If you go through, okay, it should be earlier, okay.
Earlier.
Yeah, I think you look good, okay. No, that's too early. That's too early.
Okay.
I think 2019, 2018, something like this.
Oh, maybe 120, number 120.
Formation, sediment, transportation, time dependent. No, that's not a one.
No,
That's not a one. It's
100, number 120. No,
No,
go down. Go
Go
down.
down.
No.
Before that,
120. 120.
120.
Yeah,
Okay.
120.
This one?
No, 120. Number, yeah.
yeah, open this one, see? Yeah, this one. You open this one, see? Yeah,
Wait a
yeah,
second. It's
that's
loading.
the Gucci, you see? That's one. Yeah, no, this one, just for 2015 one. You cannot download?
Yeah. That's down.
Okay, it's JGR. You look about the equation, let me see that.
Mhm.
Equation. Okay, the stress here. So then you look at the equation. You can make it bigger. Yeah, go down. They have a whole 1D equation. That is a Gucci. Yeah, that's the data EVG. So then you look about this. That's a comparison. So then you have a one. Okay, they didn't include a 1D model. Okay, let me go down. Probably in the appendix. Go down. Okay. Probably in the appendix. Okay. Oh yeah, here. Here. Okay, go down. Yeah, here. This one 1D. Yeah, you see. No, go up. Yeah, this one. Okay, approach. You see, no, you go fast.
Okay. Here.
Determine 7 to 10. You see here? That's the model. Okay,
Okay.
that's the one-dimensional model. Integrated
see.
vertical service.
Mm. Great.
All right.
Okay.
Let's
Very
walk down. But the girl was here as a
Mhm.
postdoc
Yeah. So he is now in Shanghai.
in Shanghai. Yeah.
Okay.
Yeah, we can ask him, invite him to come to give a
Yeah.
lecture, so that should be no problem.
Right.
But once he's available, okay. Because
Okay.
the time we are meeting is 8:30. It's the time about 8:30 was in China.
Actually, 9:30 in China. No,
9:30 in
8:30.
No, early morning.
Oh, I see.
Yeah, we are in the night. They are morning.
Okay.
I thought 9:30 or the 8:30.
It should be 8:30 to
I
9:30
probably
in
ask him to
China.
kind of wake up earlier, make sure he's available. If
Mhm.
not, we can maybe change the time.
Mm-hmm.
So
Yeah.
ask him to answer the question first, okay?
Okay.
Okay. Good. Okay, we stop, okay?
Mhm. So thank you so much for joining this discussion. So I will ask the unanswered questions and post the answer on the discussion board. And meanwhile, I will send invitation to Dr. Ge. Hope he will come next week. And thank you so much. See you next week. Bye.
See you. Bye.
Thank you.
Thank you.